Now, another way in which functions might present themselves is where functions are presented as the quotient of two smaller functions. Now, unsurprisingly, we call this the quotient rule. If we imagine a function f such that f was composed of one function, let's call it g, divided by another function h. Now, another way that we can write this in, I suppose, closer to layman's terms is imagine if we had y equal to u over v, where we've got u being our function at the top and v being our function at the bottom. Well, we know that we could find its derivative by doing the derivative of the whole function f by doing the derivative of g times h minus the derivative of h times g, all divided by h squared. The order here is really, really important. And so if we imagine this in terms of u's and v's, then we can say that we always differentiate in alphabetical order. So that we could find the derivative here, let's just say dy dx is being equal to, let's say, u dash v minus v dash u all over v squared. And so if we just think differentiate in alphabetical order, we won't often get this wrong. It's a little bit more difficult than the product rule in this respect, because the product rule being separated by a plus, the order doesn't matter. Here, it certainly matters which one you call u and which one you call v. So just think v's on the bottom, because we're thinking reading top down alphabetical order. Putting this into context of an example, find the derivative of f of x, where f of x is equal to x divided by 2x minus 1 squared. So our function for u in this case, we might call x, and our function for v, 2x minus 1 squared. So if we start simply by labelling what our u and v is. Label u and v. U equals x and v equals 2x minus 1 squared. If we differentiate these parts, just like we did with the product rule, u dash is equal to 1, v dash is equal to 2 times the derivative of what's inside, which is also 2, times the bracket, 2x minus 1, less 1 order, to the 1. So v dash is equal to 4 outside of 4x minus 1, which if we expand, 16x minus 4. Now with the product rule here, we might choose just to stop here with all our labels, but we know that our formula also calls for a v squared, or a denominator squared, so it might be worth me also saying v squared equals 2x minus 1 squared all squared. That's just going to be 2x minus 1 to the power of 4. We can sub this into our formula. We know that f dash of x is equal to u dash v minus v dash u, remember to differentiate alphabetically, all over v squared. So if we're thinking what are all the pieces we have here, well, my v squared, 2x minus 1 to the 4, my u dash v is 1 times v, so that's just going to be 2x minus 1 squared, and we are minusing my u times v dash, or v dash times u, which is going to be 16x squared minus 4x. Now I'm going to put that in brackets here, as people commonly make this mistake. Give ourselves a little bit more room, and we'll notice that when we expand that out, we get 2x minus 1 squared minus 16x squared plus 4x. So So that subtraction needs to go to every term in the bracket. And that's still over 2x minus 1 to the 4. Now it would be okay to leave our answer like this, although generally speaking we'd want to make sure that we could expand the top, and just to double check that there's no clear way of factorising that and perhaps simplifying our answer. So if we expand the first term here, we'll get 4x squared minus 4x plus 1. Then we've got the minus 16x squared plus 4x. We can see here that the 4x's cancel, and we get negative 12x squared plus 1 as our denominator. So just to simplify here, we would say that it's 1 minus 12x squared, nicer way of writing that, and that's divided by 2x minus 1 to the power of 4. What did we find, just to make our answer clear, was f dash of x. We can see another example here where we're asked to find the derivative of x over the square root of 2x squared minus 1. So stating our u is a little bit clearer here. Oops, just get my pen out. U is equal to x, just that first function, and I'm going to rewrite v so that it's a lot easier to differentiate. Rather than being the prime root of 2x squared minus 1, I'm going to say that v is equal to 2x squared minus 1 to the power of a half. When we're differentiating this, u dash, again, is quite simple. It's just going to be 1. But v dash actually requires a chain rule here. So if we drop the half down, we'll get 1 half times the derivative of the inside, which is 4x, times the bracket 2x squared minus 1 to the 1 half minus 1, which is to the negative 1 half. So v dash is actually equal to 2x divided by the square root of 2x squared minus 1, giving our answer as a positive index. We also know that we need to find v squared. Now, if v was the square root of 2x squared minus 1, then v squared is just 2x squared minus 1. We'd get rid of the square root. If we're plugging this into our formula, we know that f dash of x is equal to u dash v minus v dash u all over v squared, remembering to differentiate in alphabetical order. So u dash times v is just 1 times the square root of 2x squared minus 1. So we just have that as equal to 2x squared minus 1 to the half, or the square root of that. Then we're subtracting v dash u, so this fraction times x, so we get 2x squared divided by the square root of 2x squared minus 1. And that's all over 2x squared minus 1. For the purposes of our understanding here, I'm just going to put that in brackets, being to the power of 1. Now to simplify this fraction, it might seem a little bit tricky, but we think the only real problem here is this denominator of 2x squared minus 1 to the half. Sorry, this is the only real issue that we have. So let's multiply the entire fraction by 1. Or, more usefully, 2x squared minus 1 over root 2x squared minus 1. So I know that my power down the bottom, if I'm doing 2x squared minus 1 to the half times 2x squared minus 1 to the 1, ends up being to the power of 3 over 2. So that's dealt with that. I know that if I'm multiplying root 2x squared minus 1 and dividing by the same thing, that now cancels. And if I multiply 2x squared minus 1 to the half by itself, that will cancel as well. So on the top line here, I'm left with 2x squared minus 1 minus 2x squared. So these things here will cancel, and we see it simply breaks down to negative 1 over 2x squared minus 1 to the 3 over 2. It's important to make sure our notation is consistent with the demands of the question, which is f dash of x is equal to that. Our last example here, we've got find the derivative of f of x, where f of x equals cos x divided by x squared plus 1. So following our same method, let's start with u being equal to cos x and v being equal to x squared plus 1. If we differentiate these components, u dash is equal to negative sine x and v dash is equal to 2x. Now the last thing here is to think about v squared. I'm going to make a really big reminder here that x squared plus 1 squared is not equal to x to the 4 plus 1. I'm also going to highlight that. Please don't do that. We know that v squared is x squared plus 1 squared, and if I wanted to expand that out, that would be x to the 4 plus 2x squared plus 1. But right now let's leave it in brackets. We know our formula, u dash v. Let's actually rub that out and fix that right up. So we've got u dash v minus v dash u all over v squared as our goal. Well, u dash v is going to be x squared plus 1 times negative sine x, just a nice way of writing that, minus v dash u minus 2x cos x. And that's only one term, so we don't have to worry about brackets there. All divided by v squared, which we know as x squared plus 1 squared. Now there isn't really anything overly common here except for that negative 1 at the top, which might be worth taking out as a common factor if we wanted to. And we'd have x squared plus 1 sine x plus 2x cos x, all divided by x squared plus 1 squared. That's it. To go over our strategy again, whenever we're looking at quotient rule questions, we have to first label u and v. Then we need to find u dash, v dash, and v squared. We sub it into our formula, and we simplify our answer. Now remembering that the question asks us to find the derivative of f of x, so notation here is important. We don't want to see a dy dx. We want to clearly state f dash of x is equal to that. So your final step could be to contextualize your answer.